Welcome to today's deep dive into the intriguing world of particle physics. In this episode, we're exploring a mind-bending question: can a particle exist that is neither matter nor force? Grab your thinking cap and let's unravel this mystery together. Now, let's dive into something fascinating. In the vast universe of particles, we encounter two main types: fermions and bosons. Fermions, like protons and electrons, form the essence of what we see as matter. Bosons, like photons and gluons, on the other hand, are the messengers carrying the fundamental forces across the cosmos. It's a neat division, matter and forces, shaping the dance of the universe. But what if there's a twist? What if there are particles that blur these lines? Enter anyons. Theoretically, these particles are neither pure matter nor pure force carriers, and they might just have some mind-blowing applications. Our universe keeps things relatively simple with just bosons and fermions. Yet, imagine a scenario where the possibilities are endless, where countless types of particles exist beyond our current understanding. Let's revisit fermions and bosons for a moment. One key trait of fermions is their exclusivity. No two fermions can occupy the same quantum state. If you try to bring two electrons close together while they're spinning in the same direction, they push away, a phenomenon known as quantum or degeneracy pressure. It's this force that keeps you from falling through your chair. Bosons, however, are the social butterflies of particle physics. They have no issues sharing the same state. This communal nature allows light beams to intersect without disruption and makes the wonders of laser technology possible. But why this difference? Well, it's all about the spin of these particles, which we've explored in previous discussions. Stay tuned as we delve deeper into this particle puzzle. Let's break it down. When you swap two identical fermions, something really intriguing happens. There's a phase shift in the wave function. Imagine two waves falling perfectly out of sync. That's what happens here. If both fermions are in the same state, the wave functions of the swapped and unswapped pairs cancel each other out. It's like they completely vanish. Quantum mechanics doesn't allow this to happen. So, what does occur is pretty spectacular. A sort of force emerges that prevents these fermions from being in the same place at the same time. This is what we call quantum pressure. Now flip the script to bosons. Swap them, no phase shift. The wave function remains steady, unbothered. This means you can pile up bosons in the same quantum state without any drama. That awesome video we mentioned? It ties the spin of particles to this quirky exchange symmetry. But I'll leave the juicy details for you to discover in the video. And let me tell you, it involves bringing Einstein's theory of relativity into the mix, all thanks to the brilliant Wolfgang Pauli in 1940. Fermions and bosons are like the yin and yang of particle physics. Fermions, with their anti-symmetric exchange symmetry and half-integer spins, think 1, 2, 3, 2, 5, 2, keep to themselves. Bosons, on the other hand, with their symmetric exchange symmetry and whole number spins, like 0, 1, 2, are the life of the particle party. This swapping scenario isn't just a fun quantum quirk, it's foundational. It's the standard way we explain the difference between fermions and bosons, and it's crucial for understanding the forces at play in the quantum world. Diving deep into the quantum world, the discovery of particle types in mathematics seemed straightforward initially. But here's where it gets a bit tricky. The concept of swapping particles sounds clear-cut in theory, right? We envision two particles gliding towards each other, maybe even passing right through. But in the quantum realm, things aren't so simple. Due to the uncertainty principle, we can't pinpoint an electron's position with absolute precision. What if these particles just come extremely close and then veer away? When particles are indistinguishable, it's impossible to tell if they've swapped places or merely brushed past each other. It becomes unreasonable to even think of assigning fixed labels to individual electrons. This puzzling scenario led John Magne Linnaeus and Jan Myrheim in 1977 to rethink how we understand fermions and bosons. They questioned the very idea of naming electrons, and in their groundbreaking work, introduced us to a whole new type of particle, the anyons. Imagine we're in a one-dimensional universe, where our entire space is just a line. Here, two electrons move towards each other. In this simplified scenario, we can track each electron with just one variable. Now, picture a plane where every point represents a possible location for our two electrons. We say, here, electron 1 is at position 1 and electron 2 at position 2. But here's the twist. In the quantum world, this is indistinguishable from a situation where electron 2 is at position 1 and electron 1 at position 2. In fact, this entire scenario across the upper half of this plane is a mirror image of possibilities, reflecting the fundamental quantum indistinguishability. As our electrons dance around each other, they trace a path through this configuration space. But here's where quantum mechanics throws us a curveball. What happens when our path hits the diagonal border of this space? This border is critical. It represents our electrons getting so close that telling them apart becomes impossible. If they continue past this point, it would have shown up in the part of the map we deleted. They might just pass each other, or they might deflect off one another. But in the world of indistinguishable electrons, these possibilities merge into one. Whether they pass by or bounce back, it's all the same in our simplified model. So any path that reaches this boundary essentially reflects back into our existing space. Now, let's add a quantum twist. Instead of thinking about particles, we consider the wave function. This wave function isn't just a static entity, it's dynamic, representing the spread of probabilities for where our electrons might be. And yes, it's as wavy as it sounds, sprawling out over our configuration space like ripples in a pond. When our wave function meets the boundary, it doesn't just stop, it interacts with this edge, reshaping and adapting, much like a wave adjusts when it hits the shore. This edge, this boundary in our configuration space, plays a critical role. It guides the flow and form of our quantum wave, echoing the complex, intertwined dance of our electrons. Picture this. Our quantum universe is buzzing with activity, where the value of each point in our wave function is delicately influenced by its neighbors. This entire dance evolves over time, guided by the rhythms of the Schrödinger equation. Now, let's zoom in on our two-electron wave function. To really understand it, we impose a special condition. It must return zero probability of finding electrons on the forbidden side of the boundary and reflect perfectly off this quantum barrier. When the wave function hits this boundary, something remarkable happens. It doesn't just bounce back. It comes back with a twist, a phase shift, which fundamentally alters its quantum state. Think of it like light reflecting off a surface. When light hits glass or water, it undergoes a phase shift of pi radians, or 180 degrees. For simplicity, we define the phase shift in terms of half-wave cycles, so a shift of 1 means the wave has shifted by half a wave cycle. Similar to light, the wave function of our electrons also experiences a phase shift upon encountering this abstract boundary in our configuration space. What does this mean for our electron duo? Their combined wave function doesn't just reflect, it reverses, gaining a minus sign upon reflection. This isn't just a small detail, it's a quantum quirk that profoundly influences how particles behave at the most fundamental level. Remember when we discussed the anti-symmetric nature of electrons in our last video? Well, swapping two electrons actually flips their wave function sign. Today we're exploring a fresh perspective that does an even better job because it directly addresses our uncertainty about which electron is which after they zip closely past each other. So we've effectively captured the fundamental behaviors of bosons and fermions without needing to distinguish one particle from another. But hang on. This raises a tantalizing question. Are 0 and pi the phase shifts for bosons and fermions? The only possible phase shifts? Let's draw a parallel with light and mirrors. It's possible to engineer a mirror to cause any phase shift in the reflected light. Could it be the same for wave functions at this quantum boundary? Absolutely. It turns out that wave functions can indeed experience any phase shift. Enter the anyone, particles that can manifest a phase shift other than just 0 or pi. Like bosons and fermions, anyons' exchange properties are tied to their spin, which suggests that anyons could potentially possess any spin, not restricted to half or whole integers. This revelation pushes us towards a more robust framework for understanding particle statistics. If this approach allows for any conceivable spin, why then does our universe appear dominated by bosons and fermions with their strictly limited spin values? Let's dive deeper into this quantum enigma and uncover what else might be out there, waiting to be discovered. So, based on our discussions, anyone seem likely to exist in the one-dimensional universe we've explored. But what about adding more dimensions? Let's expand our universe and test if anyone's can still make an appearance. Imagine we have two electrons moving in a two-dimensional space. Typically, this scenario would require a four-dimensional configuration space, 2 dimensions for each electron. However, we've got a clever trick to simplify things. We focus only on the relative positions of the electrons. Think of it as our axes moving along with them. What matters now is how far apart they are and their orientation relative to each other. This approach is called using center of masses coordinates, and it effectively reduces our navigation space to 2 dimensions for our pair of electrons. Now, as these electrons dance around in real space, our configuration space tracks the shrinking distance between them and their shifting center of mass. Here's where quantum weirdness kicks in again. The indistinguishable nature of the electrons makes part of this new configuration space redundant. As they zip to a point of 0 separation, it's unclear whether they've simply passed each other or bounced back. This ambiguity forces us to discard half the plane, as we can't determine which electron is on which side. And when they hit this conceptual boundary, they don't bounce back. They Pac-Man, teleporting to the opposite side. To describe their motion without them popping across the space like in a game of Pac-Man, we use a little quantum arts and crafts. We fold the remaining half of the configuration space and glue the edges together. This manipulation transforms it into a cone-like shape. Now tracking the electrons in this transformed space, their movement describes a continuous path around this cone. It's a mesmerizing quantum dance, where our two-electron system navigates through a folded world, revealing even more about the mysterious nature of anyons and their possible existence in multiple dimensions. Now, if we want to reverse this phase shift, we simply have the system retrace its steps. If the phase shift for a clockwise motion in configuration space is some value, let's call it ETA, then the shift for an anti-clockwise motion is the negative of that value, minus ET. This makes sense because rewinding the motion should subtract the phase shift that was added. In our 2D case, this phase shift can be anything, so 2D anyons can indeed exist. But what about a universe like ours with 3 spatial dimensions? For 2 particles moving in 3 dimensions, we'd need a 6-dimensional configuration space to represent it. Even with tricks like using center of mass coordinates, we'd still end up with a 4-dimensional space, which is tough to visualize on your 2-dimensional screen. So, let's simplify by restricting our particles to a 2D plane within this 3D space. When we do this, the configuration space resembles our previous 2D universe scenario. However, there's a twist when this 2D plane is embedded in a 3D universe. This extra dimension introduces new possibilities and nuances in the behavior of our particles. By exploring these different dimensional spaces, we uncover the fascinating potential of anyons and their unique phase shifts. It's like peeling back layers of the quantum onion, revealing deeper and more complex interactions. The quantum world is full of surprises, and each dimension we add brings us closer to understanding the true nature of these mysterious particles. Imagine being in a true 2D universe. You can't just turn around and see the plane of motion from the other side. But in a 3D universe like ours, you can. And believe it or not, this ability to change your viewpoint is why anyone's become impossible. Let me explain. Remember our 2D universe configuration space, a cone. Moving around the cone one way introduces a phase shift, and moving in the opposite direction introduces the negative of that shift. In our 2D slice of a 3D universe, the same rule should apply. If two indistinguishable particles pass through the same point, they pick up a phase shift. If they move back, they pick up the negative of that shift, returning to their initial state. But here's where 3D changes the game. In 3D space, we can do something impossible in 2D. We can rotate our point of view. Imagine looking at a transparent clock from the front, then turning it around and viewing it from the back. Suddenly, clockwise motion appears counterclockwise, even though the clock's movement hasn't changed. If we rotate our reference frame by 180 degrees, the motion looks different, as if reflected in a mirror. Constructing the configuration space from this new perspective, clockwise becomes counterclockwise and vice versa. This ability to change perspectives in 3D undermines the unique phase shifts of any ones that we see in 2D. Essentially, what looked like a distinct particle behavior in 2D becomes indistinguishable in 3D because we can always rotate our view and flip the motion. So, while anyone's thrive in the flatlands of 2D worlds, our 3D universe's extra dimension allows us to reframe and reinterpret these movements, making the exotic behavior of anyone's impossible. It's a fascinating glimpse into how dimensions shape the fundamental properties of the quantum world. But here's the twist. This time, we've reversed the apparent motion of the particles by changing our frame of reference, not by moving the particles themselves. So why should this affect the phase shift? After all, the quantum nature of electrons shouldn't care about which way we're facing. Two observers looking in different directions should see the same phase shift, right? But if we genuinely reverse the particles' paths, we would expect a negative phase shift for counterclockwise motion in configuration space. This seems like a contradiction. How can clockwise and counterclockwise motions both give opposite and the same phase shifts? Well, they can't. The only valid solution is that the ultimate effect on the wave function remains unchanged, making it impossible to distinguish why the rotation direction flipped. So, in a 3D universe, particle exchange symmetry must work the same regardless of the system's or observer's orientation. This restriction only allows phase shifts of 0 or pi, meaning anyone's can't exist here. Long story short, the three-dimensional world we live in confines us to bosons and fermions, maintaining consistency in particle behavior no matter how we look at it. It's a fascinating glimpse into the elegant rules governing our quantum universe. So, in our 3D universe, phase shifts must be multiples of pi. This translates to particles being either bosons or fermions, depending on whether the shift is an even or odd multiple of pi. Any other phase shift would disrupt the universe's balance, meaning anyone's can't exist in 3 or more dimensions. But in a 1 or 2D universe, there's no way to change your viewpoint to flip clockwise motion to counterclockwise. So, non-integer shifts don't cause any problems, making anyone's possible. But what's the practical use of all this theory? Besides offering a beautiful explanation for the existence of bosons and fermions, it hints that we might be able to create anyone's in our universe after all. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos, and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together, we will reach for the stars. Thanks for watching, subscribe, like, and share. Don't forget to leave your comments.